Lecture 2 covers sections 2.1 through 2.5. At the end of today's lecture, you should be able to identify active and passive circuit elements. You should be able to understand the constraints for an element to be considered a linear circuit element. You should understand the formulation of electrical resistance and how it relates to resistors. You should understand and be able to apply Ohm's law. You should be able to calculate the power dissipated in elements via Joule heating. You should be able to identify and verify ideal current and voltage sources. Let us begin by talking about circuit elements. In this course, we're going to analyze many circuit elements, and we need to break them down into two categories. The first category is passive elements. These elements can be thought of as either dissipating or storing energy. A resistor is going to dissipate energy in the form of heat. Inductors and capacitors are going to store energy in electromagnetic and electrostatic fields respectively, and diodes are going to control the flow of current. Our active elements include voltage sources and current sources, controlled sources, which include voltage-controlled voltage sources, voltage-controlled current sources, current-controlled voltage sources, and current-controlled current sources, as well as operational amplifiers. We will first focus on resistors, as well as voltage and current sources. Now, in this class, we are going to analyze linear circuit elements. A linear element satisfies two properties, that of superposition and that of homogeneity. And obviously, a linear circuit element has to exhibit linear behavior as a function of voltage and current. The superposition principle states that the total response of a circuit with multiple stimuli, or inputs, is the sum of the responses of each individual stimuli acting individually on the component. Homogeneity states that the dimensions, and subsequently units, of each contributing term are consistent. Now, let us look at linear circuit elements. Say we have an element where we have a voltage potential V across and a current I running through, and we want to determine if our element is behaving linearly. Say we have a voltage potential of 4.5 volts, and this draws 10 milliamps through it. Then if we increase our voltage potential to 11.25 volts, we see we draw 25 milliamps through it. Lastly, if we increase our voltage potential to 22.5 volts, and we see that we draw 50 milliamps through it, we can plot each of these individual behaviors. That is, if we take our rise per our run of each of these individual voltage potentials and subsequent currents drawn through our system, we see we have a constant value. Our V per I is equal to 0.45. Thus, our element is behaving linearly. Nonlinear behavior would be our V per I changes based upon our voltage potential established across our element. Now, resistors are treated as a linear circuit element. Resistors are quantified by the resistance, which has a variable R in units of ohms, which is a volt per amp. And resistance is a physical property of an element or device that impedes the flow of current, i.e. electrons, through it. Our resistance is expressed in terms of the electrical resistivity ρ, which is dependent upon the valence and free electrons of the material, the length of the element L, and the cross-sectional area of the element A, such that R is equal to rho L per A. And a resistor will be represented by the following symbol. Our resistor looks like a sawtooth pattern, where it's connected to two nodes A and B, and we have a voltage potential across the resistor that is consistent with our passive sign convention. Now, let us look at the calculation of resistance. Say we have a 30-meter length of copper that has an electrical resistivity of 1.68 times 10 to the minus 8th ohm meters. And we have two different gauges, a 12 gauge and a 10 gauge wire. We want to determine the resistance in ohms of each of these wires. For us to begin, we'll look at a 12 gauge wire. The cross-sectional area of a 12 gauge wire is 3.31 millimeters squared. So our resistance is rho L per A, where we'd have 1.68 times 10 to the minus 8th ohm meters times 30 meters per our cross-sectional area of 3.31 times 10 to the minus 6 meters squared. Or we'd have a resistance of this wire being equal to 0.152 ohms. Now if we have a 10 gauge wire where our cross-sectional area increases to 5.26 millimeters squared, we can calculate our resistance as follows. R is going to be rho L per A, where electrical resistivity has not changed. So we have 1.68 times 10 to the minus 8th ohm meters times the length of 30 meters per now in a large cross-sectional area, 5.26 times 10 to the minus 6 meters squared. and our electrical resistance decreases to a value of 0.096 ohms.